One of the theorems that we're going to go over today is the axiom of completeness, which states that every non-empty set of real numbers that is bounded above has at least an upper bound. So you can think of this as we have a set of real integers, let's say from 7 to 14. So that is a set of real numbers that is non-empty. So the axiom of completeness says that every non-empty set of real numbers, which this is, that is bounded above, so it has this upper bound, has a least upper bound. So we have this number that we can't go above, and then we also have this number that we can't go below. So there's this idea that of these bounds that we can see from this axiom of completeness. And you can sort of think about this axiom of completeness as what is the property from which I can look at whether a set is complete or not. So that's where the term complete comes from, is in what way can I think of this being as the least upper bound and the highest upper bound, right? And so those two, you can think of these are the ranges that define what complete means for my set. So that's the axiom of completeness. How can we define what is the definition of completeness within this set that we have? And so when we look also at exam FM, one of the main things is time management. You have to make sure that you're managing and allocating a specific portion of time to each question. If you do realize that you're spending 5 minutes, 6 minutes on a single question, it's essential that you move on to the next question, because ultimately you will realize that one of the main games of this exam is managing your time properly. If you fail to do so, if you waste too much time on a single question, it could turn out that that ultimately is a pilot question that really doesn't even count towards your actual score. So one of the main techniques and key things you want to keep in mind is that if you don't know the question, immediately skip it. If you don't know how to do a question, even after just reading at it, you want to immediately skip it, move on to the next question, and then come back to it. It's way more easy to get a question right the second time looking at it than to spend 10, 15 minutes trying to solve that one question, and you may not even get it right. And again, it might be a pilot question at the end of the day. So time management is very important, that you move on to the next question when you're spent like a good portion, 5 minutes working on it. Next is these beginning and end terms must be viewed carefully. So there's a lot of these word problems where you have the term at the beginning of year five or at the end of year four. You want to make sure that you're looking at those words carefully, draw out an entire diagram, and you want to make sure that does the beginning of year one really mean the beginning of end year one, or is it end of year zero? And so you want to make sure how you're structuring your time diagram. If it's like two different annuities, making sure that you have the set payments correctly labeled in such a way that you know what the beginning and end terms are referring to. You're not just, oh, saying, okay, it's beginning of year one, we're just going to make this at year one. Because it could also be at the end of year zero or beginning of year three, end of year two. So you want to make sure you're very cognizant, you're very aware of the fact of whenever you see the beginning or end terms. And then obviously the goal is to get an answer choice for every single question. Obviously the name of the game is you want to move forward during the exam if you're stuck on a question. So ultimately the goal is if you're able to get a valid answer choice for all of the questions and you don't have to sort of guess on any question, that's the ultimate goal. Just purely based on the time of the exam, it's very unlikely that you're going to go through the entire exam twice, or you're going to go back to a question to like check over your work. So checking over your work, you can always forget about checking over your work just purely based on the time, the amount of time that you have for the exam. So the goal is to get to a point where you have an answer choice for all of the questions. And if you're able to do that, then you'll be able to maximize your score. Second is sort of another concept is proof by contrapositive. So we talked about proof by induction, how proof by induction works. We went through the example of proof that the sum of these, the first n integers is n. We proved that formula, and the way that we did that, we said that if this works for the base case, and then if this works for k integers, and it also works for k plus n integers, then because we've shown it works for the base case, and because we've shown that it works for k integers and k plus n integers, we can extend that forward, right? That's sort of the recursive step, is if it works for one, also works for two, also works for three, because it works for the base case, and because if it works for k plus k, it also works for k plus one. Because we've shown that it works for all of the integers. So that was proof by induction. Proof by contrapositive is another type of proof. So instead of just proving the statement, you prove an equivalent statement, but you prove it's contrapositive, which is logically its equivalence. So if I say if P then Q, its contrapositive would be if not Q, then not P. So if I refer to a statement, let's say if a number is divisible by 4, then it's also divisible by 2. Its contrapositive would be if it's not divisible by 2, then it's not divisible by 4. So that's the contrapositive. If P then Q, contrapositive is we want to prove if not Q, then not P. And again, they are logically equivalent. So if you prove the contrapositive, you're essentially proving the original statement. So how can we prove if not divisible by 2, then not divisible by 4? Well, we can assume that if it's not divisible by 2, then the number is odd. If the number is odd, then we know it cannot be divisible by 4 because all multiples of 4 are even. So we need to prove that if it's not divisible by 2, then it cannot be divisible by 4. So that's the entire purpose of proof by contrapositive. Whenever we're given a statement, we want to look at how many different ways can I prove this. It may be easier to prove it directly. It may be easier to prove it using induction. And this is another tool that you can use to prove a statement by converting it to the contrapositive and then proving the contrapositive instead of the actual statement. But logically, you have to understand that these two are equivalent. And then a couple of different project ideas. So the first one is we went through like HTML, CSS, beginner projects. Like you just create a button. Maybe it's like a LeetCode question that you could enter in like a list, and it gives and a target gives you, okay, what are the indices of the two numbers that add up to the target, like two sum, or you can think of this as like merge intervals. That could be another question where you provide like a 2D array, merge all of these intervals. Or you can essentially any LeetCode question, you could to convert that into like a JavaScript web app. Another is an animation type project where you could possibly have like a maze that you're solving, or like a Sudoku or a word search, or any type of game where you're going from one end to another end, where you're either moving your mouse or you're pressing buttons. You could that entire concept, you can transform that into a graph. Think of that as a graph, and then use DFS, BFS, a lot of these Dijkstra's, a lot of these shortest path finding algorithms to make it more interactive. You can probably make a challenge to, okay, who can find the shortest path the first? And whoever does that, that could be a game in itself. So there's many different project ideas that you can get just from this animation type game. And you can also do BFS and DFS on literally any graph, and you can make anything any graph, right? So there's so many different creative options that you can do in regards to the creativity of these projects. Next is reinforcement learning. So there's many different terms in reinforcement learning. First, we have the agent. So the agent is the bot or the robot that actually makes the decision in the environment. The second is the environment. So the environment is what's giving the feedback to the agent. So if the agent makes a decision, makes a choice, the environment is what's going to give it the reward or the punishment or the penalty. Then we have the state, which is a representation of the situation of the agent in the environment. So this could be, for example, the position of a bot on a chessboard, or this could be perhaps if you're playing against an AI, it could be the AI's position in like a Connect 4 game or on a chessboard. Or if it's learning to, let's say, do facial recognition, it could be at what point is it able to recognize faces. So that's the state. What's the representation of that agent? What's the situation of that agent in that environment? And then the action is what the agent chooses to do to change its state. So the agent state could be its position on the chessboard. Then the action that it takes, so moving a certain way, moving the position that it moves to next, that is the choice that the agent takes to change its state. That's what we refer to as action. Then for every action, there is a feedback that is given by the environment. So we have this idea of reward, which is the feedback that the agent receives after taking a specific action. So this could refer to how good or bad the action was in achieving that specific goal. This can refer to the amount of reward or penalty that is attained after performing this action that is given by the environment. And then we have the policy function that the agent follows to determine what action to take. So you can think of this as what is the strategy that the agent is following to take on the next action to change their state. And so we have these different ideas. I'll go over a couple more. So we have the value function, which refers to the estimation of how good a particular state is. So going back to the example of a bot on a certain position in a chessboard, understanding or creating a numerical estimation of how good is that position relative to the ultimate goal, which is to win the game. How good is that position of the bot in overall winning the game? So that's the value function. And the objective of the agent is to maximize this value function. And then the Q function is the estimated expected reward of taking an action. So again, action is the choice that the agent makes. So for example, if the agent decides to move to this next position on the chessboard, what is the expected reward, or what's like the change in expected outcome of that action? So obviously you want to have a high expected reward whenever you're taking an action. That's the goal for the agent. And so again, that's very high level of what reinforcement learning is. First, the agent is in the initial state. This could be randomized. This could be set by some human controller. Then the agent chooses specific actions from the current policy. Again, the current policy refers to the strategy of the agent that the agent is following in order to perform an action. Then we have the environment providing feedback to the agent, and this feedback refers to the reward or the penalty that the agent is getting. Next, we have the agent actually updating its knowledge from the new reward, and it's changing its state. Then we have this iterative process where the agent repeats and it interacts with the environment again and refines its action to maximize the total reward. So these are the 5 steps at a very high level. Agent is at an initial state. Then the agent chooses the action from the current policy or the strategy. Then the environment provides the feedback. If it's a positive action, gives it a reward. If it's a negative action, then there's some penalty associated with it, and that changes the new state. That gives the agent a new state. Then the agent updates its policy or its strategy based off of the knowledge that it was able to attain from the new reward. And then we repeat this process. So a lot of this is similar to in reinforcement learning and even psychology, how we have positive reinforcement, negative reinforcement, humans being motivated by negative reinforcement or punishment, or rewarding good behavior or punishing bad behavior. A lot of this reinforcement learning is motivated by the psychological tendencies and even how humans actually learn. Next, we have convolutional neural networks. So you can think of a convolutional neural net as, why do we have CNNs in the first place? We have convolutional neural nets in the first place as an algorithm to detect an image. So this image could be if you're detecting, for example, facial recognition, if you're detecting if someone has like a mask or not, if you're detecting cars, if you're detecting any pieces of segments on a particular image. That's what this algorithm is used for. So first, how are we able to represent that image? So obviously any image can be represented as a matrix. So a 3D matrix, your RGB values. Then the convolution part comes in when we apply this filter or kernel. So this filter or kernel, you can think of this as another matrix. You can think of this filter or kernel as another matrix that represents features of let's say if you're doing a facial recognition, it could represent features of a face, such as a curve, some certain edges, certain facial expressions. So those features, you can think of those as these filters or kernels that are represented in matrix format. So what you can think of this is, there could, just as a simple example, this could be a filter for, let's say, recognizing a certain edge, and this can have like 103, 246, right? This would be the associated filter for that specific feature. And we slide over the entire image using this filter. And then we perform element-wise multiplication to get the influence, how strongly is this specific feature on each location of the image. So when we do this convolution, or when we slide over this kernel throughout the entire image, we get an idea of how strong is this specific feature in each location of the image. And so this is going to tell us that in this part of the image, this feature is particularly prevalent. In this part of the image, this feature is not as prevalent. And so by doing this filtering or this kernel that is going to slide over the image, we're able to get a representation of how much of this feature is actually associated with this image. So that's the entire idea of filtering or kernel why we have in the first place. Again, very high level, but the math is essentially it's a matrix multiplication over a bunch of matrices that represent an image. Next, we have ReLU activation function. This is all about adding nonlinearity. So all of this matrix multiplication that we talked about, these are linear operations. How are we able to add nonlinearity to this entire model? We're able to do that by having this ReLU activation function. If we didn't do that, then we would only have linear transformations and our model would not learn more complex functions. Fourth is we have pooling, and this is where we use the max or the average of the feature map, and we take that in order to create a more smaller downsampled feature map in order to make our model more efficient. So this is very useful when we have a large matrix, when we have a large kernel, or where we have a large matrix representation. We don't want to feed all of that into our model because it's going to be computationally expensive. So how are we able to only take the most important pieces of information? We're able to do that through max pooling and average pooling by taking these maximum of the 2x2 matrix of the feature map for each portion of the image, and we're able to do this through pooling. So again, high level, these are what convolutional neural nets are. Again, very useful and a very common algorithm in image recognition, facial detection. Anytime you're trying to identify a certain piece of image, this algorithm is pretty useful. And again, at the crux of this are neural networks, gradient descent, how gradients work, and also matrix multiplication and linear algebra. So that was it. I'll see you in the next video. Thanks.